In this video, we're going to use what we learned about intermolecular interactions and apply all of that knowledge to solubility. The general rule of solubility is like dissolves like. That means that molecules that have similar intermolecular interactions are likely to be soluble in one another. For example, sucrose has lots of OH groups on it. These OH groups can hydrogen bond and thus make sucrose water soluble. THC, which is a chemical found in marijuana, has one OH group only. Even though it has one OH group, most of the rest of this molecule is carbons and hydrogens. So in this case, induced dipole interactions are more significant for THC, and thus that makes it very fat soluble, as fats also have a lot of induced dipole interactions. Here's an example of two solvents that are considered to be immiscible or insoluble. Hexane, for example, has lots of carbons and hydrogen bonds, so the key intermolecular interaction for hexane is induced dipole interactions. Water, however, can do hydrogen bonding. So hydrogen bonding is the most significant intermolecular interaction for water. Keep in mind that water does also have induced dipole interactions. They're just not that significant because hydrogen bonding is so much more important. So if you were to mix water and hexane, you would get minimal interaction between the water and the hexane molecules. They didn't depict that very well in this picture, but what you would see is two layers, a water layer and a hexane layer. Now let's take a look at two miscible or soluble solvents. Ethanol is shown over here on the left. Ethanol can do hydrogen bonding, and that's its key intermolecular interaction. And here's water again. As I mentioned on the previous slide, hydrogen bonding is the most important or significant intermolecular interaction for water. So if you mix ethanol and water, you would get a solution where the water molecules can be hydrogen bonding with ethanol and ethanol can be hydrogen bonding with water. So these would mix perfectly and you'd end up with a solution. And hopefully this makes sense if you've ever had an alcoholic drink. Obviously a large component of beer, for example, is water. In a lot of cases what we have are molecules that are maybe partially soluble or partially miscible with one another. In the case of MTBE, which we saw back in nomenclature, we have something that has dipole-dipole interactions, but it also has a lot of carbons and hydrogen bonds over here. So what ends up happening with MTBE is that it's only partially soluble in water. It can interact with water a little bit because it has that dipole, but it also has a lot of induced dipole interactions that prevent it from being super soluble or super miscible. This water solubility number here tells us that you can have up to 26 grams of MTBE in a liter of water. And beyond that, if you add, say, 30 grams of MTBE to a liter of water, you'll start to see two layers form. Let's also look at sucrose, which we said earlier was water soluble. Now, sucrose has lots of OH groups, which make it very water soluble, but at some point, if you add enough sucrose to a water solution, you will notice that not all of it will dissolve. So it's pretty water soluble, and that 2,100 grams can dissolve in a liter of water, but if you go beyond that, you'll start to see crystals at the bottom of your container. This table in your book is great for understanding this concept. You can see that both methanol and ethanol are infinitely soluble in water. That means that it doesn't matter how much methanol or ethanol you add, you're always going to see one solution. You won't see any layers. Propanol also is infinitely soluble. But once we start adding another carbon, once we've gotten all the way down here to butanol, now you see we have a water solubility problem. What we've done is we've added so many carbons and hydrogens that butanol is no longer completely soluble in water. You can see that the trend continues with pentanol and hexanol. The more carbons we add, the less soluble these compounds are in water. If we get all the way down to heptanol, which has 7 carbons, and now only 0.1 grams or 100 milligrams is soluble in 100 grams of water. So heptanol, even though it can hydrogen bond, is not very miscible with water at all. Heptanol is what we would call hydrophobic or water-fearing because it has this long carbon-hydrogen chain. Methanol, ethanol, and propanol, however, would be considered to be hydrophilic or water-loving. So a hydrophobic compound would not be water-soluble and a hydrophilic compound would be water-soluble. The term solvation refers to attraction and association of solvents with a particular solute. This results in ion dissociation. Let's look at the example shown here. If you take this molecule and add it to a solution of water, the sodium quickly dissociates from the methanoate. That's because the sodium has a positive charge which is going to interact with the negative dipole on the water. This is called an ion-dipole interaction, where the ion on the sodium is strongly attracted to the dipole from the water. The methanoate end, you can see here, has a negative charge, and this negatively charged ion, or this anion, is now interacting with the partial positive on the water molecules. This is also an example of an ion-dipole interaction. Remember how I previously mentioned that those ion-ion interactions were the strongest intermolecular interactions? That is true. However, once you have several of these ion-dipole interactions, they become stronger than just one ion-ion interaction. And that's exactly what happens in the solvation process. You've got a really strong ionic bond, and now several ion-dipole interactions are needed to break up that bond. One issue that can come up with solvation can be steric hindrance of the solvent. In this example here, you can see DMSO, or dimethyl sulfoxide. DMSO has a pretty strong dipole. Here's the negative end at the oxygen. In this case, it's interacting very nicely with this sodium ion. This is a very nice ion-dipole interaction. However, it has a little bit of trouble interacting with the chloride anion. That's because the delta plus in this situation, or the partial positive charge, is really centered on that sulfur. All of these carbons and hydrogens are not as positively charged as that sulfur, and the chloride is having some trouble getting in there and interacting with that sulfur. So these ion-dipole interactions are not as strong as these over here. And that means that sodium chloride really isn't very soluble in DMSO. Alternatively, it is very soluble in water because you don't have the steric hindrance issue. Here are some examples on how you can take advantage of what we've learned in the laboratory. For example, one of the first experiments that we do in 3301 is to separate sodium benzoate from benzoic acid. This actually works quite well because sodium benzoate, with that ion there, is very water soluble. Benzoic acid is not. Even though it can do some hydrogen bonding, you can see that because of this huge benzene ring with all of these induced dipole interactions, it's really not very water soluble. What ends up happening is when you add water to a solution of sodium benzoate and benzoic acid, is the sodium benzoate dissolves and the benzoic acid does not. So you can just filter out to separate the benzoic acid from the sodium benzoate. Another way that we use solubility in the lab is to take advantage of mixtures that aren't very soluble. You can see this cool glassware called a separatory funnel here. It's narrow at the bottom and then wider at the top, so you can see very clearly the separation of two immiscible solvents. In this particular example, we're using an organic solvent to extract iodine from an aqueous or water solution. In the next video, we're going to use what we learned here about solubility to classify solvents.